All right, so we are now recording, and I'm going to introduce our first speaker for this breakout session. So our first speaker is Gabriel Doyle, who's Assistant Professor of Linguistics and Asian Middle Eastern Languages at SDSU. He is a computational psycholinguist, which means he uses mathematical models to understand how language is represented in the mind and used in conversation. His research examines online conversation structures, the relationship between language and emoji, and shortcomings in AI models of language.
Cool, thank you. And do you know if I have permission to share my screen? Because I tossed together some slides.
Give it a try.
Let's see. Okay, looks like it's showing up, and let's get these slides going then. Okay, is everybody able to see the slides? Great. Okay, so yeah, my research, I'm a computational psycholinguist, as that wonderful intro suggested. My big thing that I was going to talk about today is how we connect text, how we collect information about what people have to say and everything, and combine that with metadata, information about the people creating the text to solve different problems. Here, when I talk about metadata, basically all that I'm talking about is anything besides the actual text itself. So that can be information about the people creating the text, demographic information, where they're from, what system they're using, anything like that. It can also be more big things outside of the individual producer. We can look at things like conversation structure, information about the audience, how many people are they talking to, all that sort of thing, as well as some sort of context for the text. This sort of metadata gives us a chance to figure out a little bit of the why behind the text. Why are people actually saying this? What is it about them? What is it about their goals? What is it about the situation that influences what they have to say? And I'm going to end up talking about 3 different projects that I've worked on to kind of give you a feel for what we can do with this metadata. So these are issues of dialect geography, understanding where in the US, for instance, people say different things, how language changes geographically. And this is where we're combining text with the metadata information of geographic location. The next is the influence of non-linguistic information. So here we're going to be combining the text with information about what time these messages were sent and information about a baseball game that was going on at the same time. This brings in some of the context and allows us to see how the world around us shapes the language that we produce. And the last one of these is to dig into conversational structure. And I don't know that we'll actually have enough time to even do a brief overview. So just in case we don't get to it, I'll just quickly mention it here. But what we're doing here is combining text with more text, what other people are saying back to us, as well as the metadata of the reply structure. Is this message in response to something? If so, what's it in response to? So the dialect geography, this is the one that has the flashiest graphics, so that's why I'm leading with it. Dialect geography, understanding why people say what they say, or how language shifts around based on where you grow up, where you're speaking. This is kind of a long-standing problem within linguistics. And the traditional way that we used to dig into this, and to some extent still do, is, for instance, calling people up and asking them what they say. So we could imagine this is based on an old experiment from, I think 96 was when they started collecting the data, and the results were published in 2006. Researchers called up 700 or so people around the country and just went through and said, hey, do you have a second to tell me how you'd say this word and stuff like that? Well, sorry, I forgot that there was that many examples here. You can imagine that we can do the same thing with tweets on Twitter. People are talking all around the country, and we can look at what they have to say and see where people are saying certain things. So you might have been able to tell from, I'll swap back to it for a sec, from this slide, that it looks like whatever's going on here, people speak in orange, some in kind of the South, and in blue in the rest of the country. Well, this was an example that I built up by looking up where people were using y'all. This is old data. You might notice that the Twitter tweets look a little out of date. So this was kind of back in 2014, I think, that I started collecting this data. The basic idea that we are getting from the Twitter data is when somebody tweets y'all, where are they likely to be from? And there's a little bit of a tricky thing here in that more people use Twitter in like major cities. So while we see a lot of examples in the dialect region, we also have to work on the fact we see a lot in basically every major city. If anybody's saying y'all, well, wherever there's a big concentration of people talking, they're going to say it there. So we need to account for some sort of a baseline on this. And we won't go into the math on how to do this. It's not too hard, but it's also not that interesting compared to the basic finding that this gives us. By focusing on this kind of baseline of where people are talking, we can sort out the examples that are coming from major cities where everybody's talking, as opposed to the places where it's an elevated level of these, specific dialectal forms. And this allows us to build up kind of a usage ratio, a sense of where people say this the most. I'll put my slides on my website or something, just in case you want to look at the full details on this. But I figured it's more interesting to just go through some examples. So here's a really stupid test case. This is I-40, the interstate that goes across the country. And it turns out if you look at where people tweet about I-40, I don't know how clearly it's coming through on your screen, but there's this orange band that matches up almost exactly with where Interstate 40 actually is. So while it's not very linguistically interesting, this is a great proof of concept. Where it's more interesting is where we look at things like how people use second person plurals. I chose the y'all example as kind of one of the most geographically best known dialectal features. You can see that y'all is in fact concentrated where you'd expect in the South. There's nothing particularly interesting about that. Again, it's a good proof of concept to show that this kind of idea works. But one thing that really has stuck with me on this is I checked the non-standard spelling of y'all with the apostrophe in the wrong place. And you can see here, this is much less concentrated in the South. Instead, we get pockets kind of throughout the country, almost as if there's a bunch of posers trying to use y'all for clout or whatever we were doing back in 2014 when I got this data. On the other hand, an alternative, you guys, is spread throughout much of the country, but it isn't really used in the places where y'all already exists to serve that purpose. And if anybody's ever been to Pittsburgh, you know that there's a very specific version of that, which as you can see is used basically in Pittsburgh and nowhere else, because who else would ever say yins? Then just to wrap up as one last example of this, especially relevant to the Northern Southern California split, there's also freeways, that's kind of interesting, but hella, you can see this is something, again, it's 2014, this probably isn't as big anymore, but at the time I was doing this as a test case, it was very prominent in Northern California, much more diminished in Southern. So that's one of the things we can do. We can bring in geographic information and tie it to text. The other big thing is looking at, in this case, it's a trade-off between linguistic and non-linguistic information. So here's a quick example. This was from the World Series, again, back in 2014 when I was kind of starting off with this. The big finding, or the big idea that we had, sorry, the tweets weren't supposed to have shown up already, but when there's low information, when nothing's happening in the game, when people are talking, they're saying more stuff to make up for this. But when exciting things are happening, when there's big information in the game, people end up producing simpler, more predictable, less informative tweets. Let's skip that one. This is kind of the big finding that we had on this. So thanks to baseball being so boring, people have come up with a bunch of statistical analyses to try to understand what makes, a baseball game interesting. And one of the big things is at bat by at bat, you can determine how much the outcome of the at bat changed the likely outcome of the game, the win probability added. And you can see here that the more an at bat has affected the game, going left to right, the more the entropy, the information, the content, don't worry about the specific way that we quantify this, but the amount of information supplied in a tweet goes down. The more something interesting has happened, the less people have to say about it because the world is already supplying information. So we don't have to supply nearly as much linguistic information. And the last example that I wanted to bring up with this is this conversation structure example. This is looking at how much information people are putting into their tweets based on how deep into a conversation they are. And the really interesting thing about this is people start off by putting a lot of information, this is what we see in the upper left, into their first tweet. And as the conversation goes on, they slowly reduce the amount of information until it drops down to a point where there's really nothing left to say. So this is the sort of thing that there was just really no way we could have gotten into without having access to text and metadata, whether it's what's happening in a baseball game, what's happening in a conversation, anything like that. By bringing in this sort of metadata, we can find this sort of structure and really, move forward with it. So that's all the kind of examples I wanted to talk about on that. Let me stop sharing my screen. And yeah, that's just kind of a basic overview of some of the things that you can do, or at least that I've done on this.
Awesome. Thank you so much, Gabriel. That was really great. I hope we're going to have time for questions at the end of both lightning talks. But for now, I want to introduce John Rawski, who's assistant professor of linguistics at SJSU, who's going to speak next. John Rawski is an assistant professor of linguistics at SJSU, where he teaches general and computational linguistics. His research generally concerns the mathematics of language and learning, applied to both natural cognition and artificial intelligence systems. His work has appeared in a variety of venues in linguistics, theoretical computer science, natural language processing, and cognitive science, such as Language, Science Advances, Journal of Language Modeling, and others. So thank you, John. Thank you for being here with us.
Yeah, thank you. Can everybody hear me all right? Can I get a thumbs up, Nick? Because yours is the thumbnail I see. All right, great. Okay, yeah, so I'm going to talk about a different topic than Gabe did. I think I'm going to present kind of an annoying problem that exists in text mining that actually is an inherent feature of human language. And so, it's our job scientifically to understand it. And it's our job as, doing things with text mining to work around it. All right, and the problem is data sparsity. Maybe you've heard of this before, maybe you haven't, but you're going to learn about it now. Okay, so what is data sparsity? It's the opposite of denseness, okay? So you can think of data as being dense or sparse. A more intuitive way to think about it is it's whenever you have a data sample and some phenomenon is rare in the data sample, okay? All right. So for example, in names. So in many cultures, names are dense. So for example, in ancient Rome, around 2/3 of men were named Gaius, Marcus, or Lucius. In modern Vietnam, around 60% of people have one of 3 surnames, Nguyen, Tran, and Le, right? So the top 14 surnames in Vietnam account for around 90% of the population. In other cultures, names are sparse. So in the United States, the top 14 surnames account for just 6% of the population, right? And in modern Thailand, 81% of surnames are unique, okay? So we see a sort of dual-pronged phenomenon of most stuff in many cultures, most stuff is relatively few of the possibilities it could be. And in others, we have, most of the variation is in a very small amount of the sample. Okay. So this gets even more profound when you start to do, word analyses of texts, right? So maybe you can guess the book that this is. It is, well, actually, I forget if it's Alice in Wonderland or Through the Looking Glass, right? But when I just make a word cloud out of the most frequent words in Alice in Wonderland, you notice that there's a lot of them that are very, very infrequent. Most stuff doesn't appear very often, right? And the stuff that appears very often is a very small subset of the words, right? I mean, right. Okay. All right. Now you'll notice there are some missing items here, right? Some words that might surprise you that I didn't include in the sample or in the word cloud, right? What happens if I put function words back in, like the or and or of or to, right? Well, then we get this, right? Now all of a sudden we have, big blue Alice here on the left, right? Has now become sort of medium-sized burgundy Alice on the right. And now the by far most far represented of the words is the, followed by and to, and etc. Okay, so what's going on here, right? This is the phenomenon of data sparsity. Data sparsity means that stuff that should show up probably as often as other stuff doesn't show up as often, and some stuff shows up much more often than it should, right? Okay, so we could ask this a general question. How much data sparsity is there in language? Is this just a property of Lewis Carroll's writing or of random names? Like, did I just cherry pick this to invent a phenomenon? Right? Well, ideally, if it was really a part of human language, you'd expect it to show up more, okay? So here's a great way to think about it, right? Well, spoiler alert, data sparsity is everywhere, right? It is everywhere in human language, and it is the root of all problems in modern natural language processing, okay? All right. So here's a way to think about it. So you can ask yourself, how many words of input does it take a child, right, to learn a native language, okay? Conservative estimates come up with something around 10 to the 7th, right? 10 to the 7 words in the first few, that should say years of life, not words of life. All right, the 10 to the 7 words in the first few years of life, okay? Now, 10 to the 7th is a big number, right? It's 10 million, so it's a big number, but how big is big, right? Is 10 million a lot, or is it a little, right? Maybe you're surprised at that number. Maybe you thought it was less, right? Maybe you thought it was not enough, right? You might have thought, well, no, children hear far more than that, okay? Well, maybe let's ask how our, latest and greatest artificial intelligence large language models do on this kind of stuff. So if you look at state-of-the-art AI models, there are some what are sometimes called neural network models of language, okay? I guess most well-known one these days is called GPT-3, okay? It has been making headlines lately. Maybe you've seen them, right? It is a, quote, deep learning model, and it is impressive on many, but far from all language tasks, okay? It's made by the OpenAI folks who are up in Washington. Right, now, how much text has GPT-3 seen in its lifespan, right? GPT-3 was trained on 1.8 times 10 to the 11th words of English, okay? So remember, we had 10 to the 7th, GPT-3 has 10 to the 11th. Now that's an exponent, so that is 4 orders of magnitude higher than the amount of data, okay? Or in more precise terms, it's greater than 5,000 times what the average 3-year-old has heard. More than an entire human lifetime's worth of language. And GPT-3 doesn't have to worry about things like phonetics, phonology, word segmentation, morphology, syntax, anything like that, okay? Here's another way to look at it, right? We can look at, stepping outside English for a moment. We can look at a language which has, a more well-developed inflection system, for example, in Spanish. So we can look at a paradigm of Spanish verbs here, right? So on the columns here, I have first person, singular and plural, or first, second, third person, singular and plural. And then I have different paradigms, right? The present indicative, future, imperfect subjunctive, conditionals, futures, right? And here are the forms, right? When you take a Spanish class, you will, be bullied with these day in and day out, right? And so ideally, we might expect that a Spanish speaker learns all of these, right? At least they should see all of them, right? So they're common in classrooms, right? Each of these forms, you will be bullied with them in classrooms, but they are conspicuously absent in the wild, right? So how many of these forms do we think a child actually hears? All right. How many forms do we think that they actually hear? Well, it's even worse. Okay. If you look at a table of Spanish verb forms, right, for a verb like hablar, the verb we just looked at, around 30% of the forms can be found in a few million words of speech. Okay, 30%. And that's often a few million words. Okay. The maximum is a verb like decir, right, to say, which is where you see around 70%. Okay, so the most, complete paradigm that you can see, you see a given form, you only see 70% of the table. Okay. And the child or whatever the agent is has to infer the other 30%. What's the average? Maybe mins and maximums aren't, so maybe I shouldn't cherry pick them. So the median one is about one form per verb. So now we can see the magnitude of the task that the child has when they come into the world trying to learn language. They see maybe one form of the verb, like suspira, and they have to predict the rest of the entire table. Okay. So what do? A speaker might never hear or produce this form, but they still know it, right? They might never hear suspiraseis, but they know it, right? So how do they do that, right? This is also a challenging task for natural language processing systems. They might never, ever hear this form, right? And yet they might have a situation where you might have it, right? Or in a given corpus, right? Whatever the corpus is, Twitter data, Wall Street Journal data, speech data, child data, whatever it is, you might not see forms that are relevant. Okay, so this can really muck up text analysis. Okay, so here's an example of where this goes wrong, right? So, when I use NLP tools like Google Translate, I often get bored very quickly and I like to see how easy they are to break. So it turns out that they're very easy to break, right? You can, they rely on a lot of statistical inference to get around this problem, which can have some funny results. So here I just took a Japanese character, right? And I just typed it in increasingly amounts of, I just typed them again and again and again, right? Now, this is gibberish, okay? But interestingly, when I translate it, right, so the speech form of it actually gets predicted pretty well, right? It just says the same thing over and over again. But when I translate it into English, I get something strange. I get this weird sort of postmodern poem, right? Now, what does this tell us? It tells us that the way that Google Translate is trying to, account for these things, right, has nothing really to do with the knowledge that is accounted for by these text data, right? It's just doing massive statistical analysis over this data based on patterns that it found in the corpus, okay? And this can lead to some funny results, right? Look, I add one character and suddenly I move from there was a bad shape, but a bad shape, to it is prone to burns, but also a burn, right? Barely anything in common. And literally all I did was add one more guy. So this is nonsense and this is nonsense. So not only is there a systematic lack of intuition here, but it's not even wrong. It's doing something worse, right? Right. Okay, so when I see things like this, I immediately want to know what happens if I just type in nonsense. So if I just type in random vowels, right? Here I just picked, I think, 3 or 4 vowels and I typed it in and I asked Google to detect what the language is and then translate it into English. It thinks that this random sequence of vowels is Hawaiian and then will then translate it from random gibberish into systematic gibberish, okay? Right, okay. But why is this happening? Right, if we look at our Spanish verbs, right, if you plot them all out, right, here I got a bunch of verb lemmas across inflection categories, right, from a giant corpus of child-directed speech, what's called the childist corpus, okay? And so I can rank them here, right? So on the x-axis, we have what the rank is. So we have the most frequent lemma all the way to the 2000th most frequent lemma. And then we have the most common inflection rank versus the 60th most common inflection. So we can plot them. And then we have the frequency, right? So I can plot frequencies, right? So what is the frequency of the most frequent item versus the 1000th most frequent item? And you notice this interesting curve here, right? There's this nice, interesting curve in both dimensions across both lemma and inflection frequency. Now, remember also, this is a log frequency. This is what happens when you take the frequency and you sort of squish it down using a logarithm, right? So what that means is the y-axis here on frequency is log. So this red stuff up here is actually 1,000 times more frequent than the blue stuff down here, even though it's represented, 2, 4, 6, 8, 10, right? All right. Okay, so 1,000 times more frequent stuff up here. What does this tell us? It tells us that most stuff in language is rare. most of the informative text that you're going to see for analyses do not show up with any sufficient frequency to make any generalization about them. All right. The stuff that does show up with any appreciable frequency is mostly the same stuff over and over and over and over again. Okay. All right. So that's a curious thing. In fact, now that we're looking at shapes of distributions, we can ask what kind of distribution does natural language information look at? Okay. So this actually has a long use history in linguistics, and it has a property called Zipf's law. So Zipf was a linguist and a psychologist who lived almost 100 years ago. And Zipf's law states that a word's frequency, right, F here, is a word's frequency is inversely proportional to its frequency rank. So what does that say? Well, let's look at this. Here's from the Wall Street Journal corpus, which is about 1 million word corpus of English, okay? So I just plotted the most common words and I ranked them from most common to like 1,000 most common, okay? So what do we see? The most common word is the, okay? All right, has a frequency of about 70,000, okay? What about the second most common word, right? So that would be R of 2. Well, what Zipf's law would predict is that R should be somewhere around 70,000, right, divided by 2, right? The most common word, the frequency of the most common word divided by whatever the rank is, okay? And lo and behold, we get somewhere around 35,000, okay? So if you graph that out, if you just keep adjusting R and F, right, you will get exactly a curve that looks like this. Now look at all this stuff. These are all the words. Look at all the words in the Wall Street Journal corpus, right? Most of them are showing up once. In fact, when I counted them up, it's about 95% of the words in the given corpus show up exactly once, okay? Now, when you start to think about sequences of words that are sequences that are 2 words long or 3 words long, right? The numbers get even more severe. Around 98% for 2-word sequences, 99% of 3-word sequences appear exactly once, okay? If you generalize this out to sentences, right? Now you start to see we're really in trouble. Okay, so it's on the one hand that it's a miracle that children actually do anything at all with data that look like this. Okay, so this is an example of a Zipfian distribution. Okay, now if you know something about statistics, you might recognize this as what's called a power law distribution, right? So the power here is R to the -1 or 1 over R. All right, so this is what's called a long-tailed power distribution. So the linguistic lesson here is that most stuff in language lives in the long tail. All the helpful stuff for figuring out verb paradigms, word frequencies, sentence analyses, dependencies, it all shows up very rarely, okay? So this is actually antagonistic for children, okay? And it's terrible for big data systems because big data doesn't help here. It makes the problem worse. Because what happens with big data? You get more data, but most of it is rare, okay? So it actually makes things much, much, much worse, okay? All right, so most stuff in language lives in the long tail, okay? That's what you can think of. Okay, now maybe you're thinking, okay, John's just cheating. He's picking up random phenomena, maybe words aren't real. Maybe I care about sentences or I care about these. Well, okay, fine. So what I did was I took that child directed speech corpus in both English, German, and Spanish, okay? And you see the same behavior in English words, German words, Spanish words, okay? And then I took a corpus of syntactic dependencies that are dependencies that hold amongst, chunks of sentences, okay? Right, and so I looked at those in a bunch of languages, Gothic, Latin, Turkish, Finnish, Spanish, German, and English, all the same thing, okay? The Zipfian distribution shows up everywhere. No matter the language, no matter the level of linguistic analysis, the Zipfian distribution is a constant plague, okay? What it means is that children actually have a more difficult task than they should. And statistically what it means is that trying to infer frequencies and distributional information right from text is a non-starter. Because most of the statistical inference techniques that work out assume that the data follows what's called a normal distribution. And a normal distribution means that you can use the central limit theorem. The central limit theorem says, all I have to do is sample data. I just have to take corpus data. And eventually I will uncover the true distribution of the language use, okay? But statistical distributions like these show that the task is actually much, much harder, okay? All right, so I didn't want to prattle on too much about it. I think my time's up, but since I know that there are a number of people who are at the CSU system, right? If you're interested in this type of analysis, right, we offer 2 courses here, right, both in corpus linguistics and in natural language processing. And I feel obligated to advertise our upcoming bachelor's and master's degrees in computer science and linguistics, and then in computational linguistics. So, right, I will stop talking now, and I hope, people ask me more about how mysterious this is.
Great, thank you, John. Well, it looks like we have a few more minutes for questions. Does anybody have any questions? Jill put a question in the chat, which I will read out. Jill asks, I think this is a question for John. Then shall I ask the question that people ask me as a cataloger in the library all the time? Why do they, meaning Google, etc., rely on machine learning based on often faulty or incomplete sample sets rather than hiring professional linguists, grammar teachers, or taxonomists to work with programmers to fix the code logic?
Yeah, so that's a great question. So surprisingly, the answer is that they do both. They do have teams of programmers who are, trying to implement different machine learning techniques. But what they've come to realize over the last 20 years of having the most sophisticated statistical inference mechanisms known to mankind is that they need to hire domain experts, okay? So it is actually an extremely common career path for people who study computational linguistics to then go into work with the programmers, especially with regard to particular languages or even, domain general language stuff. If they're trained in linguistics, they can be absolutely a benefit, okay? And Google and Facebook and all the FANG companies, whoever, have realized that, yeah, one can't just infer your way around the problem, okay? Now, there are statistical techniques to figure this stuff out, right? So there are ways to kind of, maneuver your way around the problem. One thing that I thought about talking about was that, if you try to categorize, say, words according to, you give them little, I guess they're sort of metadata labels like Gabe was talking about with things like noun or adjective or verb, right? So within those categories, Zipfian distributions become normal distributions, okay? And so in fact, if you take a big corpus that looks Zipfian and then you categorize everything out by part of speech, right? You will often get normal distributions. So the idea here is that why do these categories like verb, noun, adjective, etc. exist, right? Well, one answer is that it helps the statistical inference problem because you're able to analogize within categories. But if you don't know something about linguistic information, you're just totally out of luck. You have to treat a word like the in the same category as like, an inflected verb like runs, right? All right. So this is a way in which, yeah, both can, they need to work together, and they do work together. And when it does happen, good things happen. When they don't work together, bad stuff happens.
And a little follow-up, can I ask? I had at one point been told that Google in particular was doing a lot of this. Their sample set was based on the Google Books project in a lot of cases. Is that accurate?
That's probably true. I mean, they monitor so much data. It's shocking. I mean, like the amount of data that they have is so large that it's not even worth asking where, exactly which source it came from, because often it's a blend of sources, right? They're using speech data, which is then transformed into text, which is then used in composition with some other data, which starts out as text, and then gets mixed up in everything, okay? So they're huge, and, depending on which team one works with, you will deal with different types of stuff, each of which has its own challenges. The speech corpora are different than the Twitter corpora, right? Which are different than the videos plus speech corpora, which then maybe have some annotation attached. There's all over the place, right? I wouldn't be surprised if at one point they were taking everything from Google Books, but now, given that they have access to the entire web, plus everybody's search history, plus everybody's attempts at search history, plus adjacent data partners, I mean, it's so like what's her name from Harvard calls this, surveillance capitalism, in the way that like there's just so much ever-present access to data and metadata that it's often not worth looking at where the data comes from, particularly rather than how the data behaves. Right?
Interesting. Thank you.
One thing I will say is that the English data is far more represented than any other language data, right? So even when you look at the representation of languages, even at the level of like entire languages, there's Zipfian distributed, because the amount of stuff that we have, say for English, French, or Spanish, when you can, compare it to a language, even like Indonesian, right, which has a ton of speakers. I mean, the data and the coverage of the data is just so vastly different that the methods, it almost looks like different systems.
All right, we have 2 minutes left. Does anybody have any further questions? I can ask hopefully probably not a 2 minutes question, but I'll try. I'll throw it out there. How can I feel like there's a lot of public discussion about how far along are AI systems, or how good is natural language processing? How can non-specialists try to understand some of these conversations? Or is there something you would say to, people outside the field about where the status of those developments are?
I could say something, but if Gabe wants to, in my
No, feel free.
In my personal opinion, they are extremely brittle. So I mentioned there are some tasks that they work extremely well on, but remember, they're tasks that humans designed because humans want them to do this particular thing. So, maybe taking recorded speech and then asking what is the most likely text that, corresponds to that speech utterance. Okay, that is a very specific task. And AI systems are very good at that because they've been working on it for 40 years, right? There are other extremely basic tasks that a 3-year-old knows how to do that the systems are woefully inadequate at, okay? So now, given that there's so much industry hype around it, the stuff that they work well at is hyped, and the stuff that they don't work well at is diminished. So there's a lot of, imbalanced coverage of this stuff. But yeah, it's in no way close to being, quote, solved, right? And in fact, my students all the time are like, I feel like I know less about this, but I have more skills to deal with it. And that's kind of the paradox of working with computational linguistics, is there's a ton of tools, but the mysteries just keep compounding. You're muted.
Thank you both so much. That was great to hear. And I think we're going to go back to the main room, and I hope everyone sticks around for the next set of breakout rooms. So we'll go back and they'll kind of say what's in what room. But thank you to John and Gabriel for being part of this, and thank you for everyone for attending.